All right, so today we're going to be taking a look at implicit differentiation. So this comes in handy when we can't write the thing we're dealing with in the form of a function. So notice that everything we've dealt with so far could be written in the form of a function. That is, we can write y explicitly in terms of x. So one example of this would be y equals x sine x. Here's a function right here, and the y we can see in the equation is explicitly written as a function of x. So you pick an x, and once you've picked that x, y is determined, right? It's this whole idea of dependent, independent variables we've dealt with in the past. Well, sometimes you can't write things in that way. So one example of not being able to write things quite cleanly in that way would be a circle. X squared plus y squared is equal to 9. If we go to solve this for y, we don't get a single function like we do on the example we just looked at, right? Now, you can break this down into two separate functions. So we know that we can break down a circle by solving for y into the top half and the bottom half of the circle. So if you were just interested in the derivative of the top half of the circle you wanted, you could just do this. You could break it into the top half and then just work with the top half and do whatever you're trying to do. So that is definitely an option available to you sometimes. But there are times when even this is not really feasible. So we have to bring in what's called implicit differentiation. That is, we can go through and we can differentiate the equation even when it's in this form like this, x squared plus y squared equals 9. It's not being written in the form of a function, but we can still get at those derivatives. Okay, so let's go through and try to figure out what the equation of the tangent line would be at x equals 2. Okay, so that's our goal. Okay, so we want to find the equation of the tangent line at x equals 2. How exactly are we going to go through and do that? Okay, so we start off with our equation, x squared plus y squared is equal to 9. And then what we're going to do is implicitly differentiate. So the whole key to this section is realizing that for the problems that we're doing in this section, y is understood to be some kind of function of x. We don't know what that function is because we can't solve it in terms of x, but we know that it is some function of x. So if you piece that together with the chain rule, if you go, okay, y is some function of x, that means there's something going on behind the scenes where you would manipulate x's to figure out what your y is. And this would be easy if we knew what that function of x was. In this case, we don't know it. So what we're going to do is we're going to use some notation. And I'm going to do two problems, one with one notation, one with the other, so that you're familiar with both. They both come up frequently with implicit differentiation, so you have to be comfortable with both of them. Okay, so what happens is we go through and we differentiate with respect to x, but when we get to the parts that have a y in them, we have to ask ourselves, what does that mean? Okay, so when we get to here, the first part, the derivative of x squared with respect to x is 2x. So that's easy. That's what we've been doing all along. We take the derivative of x squared and we get 2x. Okay, but now it's a little bit different because you can kind of imagine this being a chain rule problem. And when you look at it at first, you go, wait, y squared is a chain rule problem? Yeah, because remember, y is some determined function of x. We just don't know what it is. We can't determine it. It is determined, like in the universe, there is some rule saying what y has to be, but we can't get our hands on it. We can't figure out what that is, so it's invisible to us. So yeah, imagine if this y was really like some parentheses and it had a function of x going on inside of it. That's really what we're talking about here, but the only symbol we have to put there is y. So even though it doesn't look like it, this is really a chain rule problem. Okay, so what do? We take the derivative with respect to the outer function. Well, that would be 2y, so that's where the 2y piece comes in. And then you take the derivative of the inner function. The inner function is y, so the derivative of that, by definition, is dy dx. So this looks weird at first. It's just the chain rule. So if you let that piece sink in that y is a function of x, and if you can kind of comprehend how this is really a chain rule problem, then you've got, 80% of implicit differentiation you've got under control. Okay, so when we implicitly differentiate this equation, we get this because the x squared becomes 2x. Here we use the chain rule to get 2y dy dx. And here when we differentiate 9, we get 0. Okay. So now what we want to do is go through and solve for dy dx. We want to know what that derivative is. That was kind of our whole goal here because we're trying to find a tangent line. We need the slope of the tangent line. That comes from the derivative. So we go through. And our next line then, we're just solving for dy dx. So just treat it like any symbol that you're going through and solving for. So I subtract 2x to get it on the other side of the equation. And then we're going to go ahead and divide by our 2y to get dy dx equals negative 2x over 2y. The 2's cancel, and we get negative x over y. So if we want to know the derivative at a point, we plug in the x value for that point, and we plug in the y value for that point. That's how we're going to get there. So, okay, how do we do this when x equals 2? We know an x value. We don't know the y value. We haven't figured that out yet. Well, that's the next thing we're going to do. Now find y when x is equal to 2. Well, let's go through and do that algebraically, and then we'll look back at the graph and make sense of it. So you just take your original equation, x squared plus y squared is equal to 9. And then what we're going to do is go through and solve that for y. So you plug your 2 in for x, which would be 4. 9 minus 4 is 5. So you can see that when we solve for y, we would get y equals plus or minus 5. Now, wait a minute. Plus or minus 5? Why am I getting two answers here? Right? What's the y value that goes with x equals 2? Well, if we go back to our graph, we can see that there's two of them. There's this 2 square root of 5 and negative 2 square root of 5. So the question is, well, what's the one you care about? We're so used to this just specifying an x value and then there's some y value that comes along with it. But remember, this is not a function. It fails the vertical line test. Therefore, when you specify an x value, there's actually 2 points that you're interested in. You might be interested in both of them. You might only care about the top one. You might only care about the bottom one. Depends on the problem that you're doing. I'm going to say let's just focus on that top one, the black point up at the top. So we'll just say that's the point that we are concerned about. Okay, so we now know that we want to deal with 2 square root of 5. That's our point. So we have our x value and our y value, 2 square root of 5. We just figured that out. So when we take the 2 and square root of 5 and plug them in, we plug our x and y into the dy dx, we get dy dx is equal to negative 2 over square root of 5. So that is the value of our derivative at the point that we just found. That is the slope of our tangent line. Okay. So that's the slope of our tangent line. We want the actual tangent line, the whole thing. So we're going to go through. We know that our form has to be in the form of a slope-intercept. So we've got y equals negative 2 over square root of 5x plus b. So all I did here, I took our equation of a line and I stuck the slope in there that we already know is the slope for our problem. Okay, now we're going to go through. Now you stick in the x value and the y value for the point that we know, and you're going to be able to then go through and solve for b. So if we finish this out, right, we go through the algebra here, we see that we're going to get a b value of 9 over square root of 5. We get a b value of 9 over square root of 5. So we can go ahead and go back and plug that into our graph. And you can see down here we've got the equation, right? Y equals negative 2 over square root of 5x plus 9 over square root of 5. And sure enough, that looks just like the tangent line we are supposed to get. So using implicit differentiation, we just went through and found the tangent line to a point on this circle. Now, it took a few extra steps that we're not used to. When we had to go through and solve for the y, we got 2 values. We had to determine which one we cared about. I just arbitrarily picked the top one in order to finish this problem. Normally, in a problem, if they say at x equals 2, you'd have to find both of those tangent lines. Usually, they're just going to have you find one, though. But it would be the exact same steps, except your y value, instead of being square root of 5, would be negative square root of 5. So you just repeat the steps that we did, but with negative square root of 5 there. All right, so let's implicitly differentiate this equation right here. So I'm going to go through. Remember, y is a function of x. We are taking the derivative with respect to x. So we have to treat everything that way. So let's go through and see if we do that. When I differentiate y, I'm going to get y prime. So this time I'm using the prime notation. It's just another way of doing it. It just means the derivative of y, just like how in our last problem dy dx meant the derivative of y. They mean the same thing. There are two different notations that are used in calculus, and they come up a lot, so you really do want to be able to recognize both of them. So that's why I'm doing one type for each of these problems. Okay, so our y, when we differentiate that with respect to x, becomes y prime. All right, and I'm going to jump ahead. I'm going to skip this term and come back to it in just a second because that's really the problem term. Of the 5 terms in this problem, 4 of them are very easy. One of them takes a little bit of thinking, and that's where the mistakes occur. So that's why I want to come back to that one in just a second. We see here the x squared. Well, differentiating x squared with respect to x gives us our 2x. Okay, that's not a surprise. And when we differentiate the constant 1 with respect to x, we get 0. So that term's just gone. And then, of course, the derivative of 0 is 0. So what's this big mess here? Well, let's go back to that xy squared part. Okay, so what do we have here? Well, we really have a product, right? We have 2 functions. We have x, and we have some other thing that is a function of x. So ultimately, what you're looking at here in the brackets is a product rule. I'm applying the product rule to this term right here, remembering that y squared is itself a function of x. Okay, so when I take the derivative of x, I get 1, and then we leave the second term the same, right? And I put all this in a bracket because notice this negative has to distribute properly to everything in the bracket. So having that bracket there helps us remember all the places that negative needs to go. Okay, then when we get into the second part, we leave the x the same, but then we have to take the derivative of the y squared part. Well, you take the derivative with respect to the outer function, giving us 2y, multiplied by the derivative of the inner function, which would be y prime, giving us 2y prime. Okay, so that's what's going on here. There's a few different steps going on here. There's a product rule taking place here, and you can kind of see that form we're used to, the 4 sets of parentheses with the plus in the middle. But then there's also a chain rule taking place, and it's a chain rule that people forget exists because for one thing, we just learned the chain rule, and I mentioned it takes a little practice to remember to use the chain rule. But here with implicit differentiation, it's even easier to miss because people aren't thinking about y in terms of x's. You have to always remember that. Y is a function of x. So we get this, okay? If you got to this point, and if you understand this, the rest is essentially just algebra. So it's just kind of cleaning things up. So if you got the part I just talked about, that's like 90% of the difficulty with this problem. You should be good to go from here on out. So now let's just clean up. We've got our y prime. Notice we have a few terms with y prime. We want to do that by getting those together and getting everything else that doesn't have a y prime away from it. And then we're going to factor out the y prime and divide by whatever is on the y prime. So basically, I've just simplified things here. We've got our y prime minus y squared minus 2xy y prime plus 2x equals 0. Okay, so just going to move things around a little bit, get the y primes on one side, the non-y primes on the other, and we end up with our 2y prime terms over here, our non-y prime terms over here, right? And then we're just going to factor this y prime out of there. We're going to get it out. Leaving us with this, so y prime times 1 minus 2xy equals y squared minus 2x. And then this looks kind of complicated, but it's just some junk, right? It's just some value that's multiplying our y prime, so just divide by that. So if we go through and divide by this, then we get our final answer, which is solved in terms of y prime. So we're looking at y prime is equal to y squared minus 2x over 1 minus 2xy. Now, if you're doing a problem where you have a point, you would plug your x in here, you'd plug your y in here, and you would now get a value for the derivative evaluated at that point that you care about, just like we did in the last problem.